Hello and welcome to our webinar, Designing for Moldability, Part 1, Design Considerations. I'm Mark Strobel and I'll be your moderator today. Our featured speakers are John Sidorowitz, Director of Operations, and Orv Bro, Technical Account Manager. John is a technically minded sales leader and problem solver in all things manufacturing. Having a degree in management and a very diverse background, John understands the entire manufacturing process from design to final product and everything in between. John has held many roles at Accentric in his 10 years here and is currently our Director of Operations. Orv is a technical account manager with Accentric. He has a bachelor's degree in plastics and polymer engineering and has 11 years in manufacturing and plastic part engineering. This presentation is expected to last approximately 45 minutes and is being recorded. There will be a Q&A session at the end of the presentation. Please use the questions field on your screen to submit your questions. This is the first of a two-part series on design for manufacturing. The second part will be held on June 17th. If you've not already signed up for part 2, a link to the registration will be emailed along with a link to the recording of this webinar within 48 hours. We encourage you to follow Accentric Mold and Engineering on LinkedIn so that you can stay up to date on our latest blog topics and webinar schedules. I now turn over the webinar to John and Orv. Gentlemen.
Thank you, Mark. Appreciate that. And thank you everyone for joining us this afternoon. On the left side of this slide here, we've got the topics that we'll be covering today. As Mark mentioned, this is part 1 of a two-part series. Today we're going to be talking about just some basic mold fundamentals, what makes up a mold, how it, the runners, gates, just some overall basics, get into tolerancing, material selection, and then some design elements, mainly looking at draft, wall thickness, corners, transitions, ribs, bosses, undercuts. And then we got a little kind of a best practice checklist at the end there to that you can print out. And with that, let's get started. Orv?
Hello, everybody. Thank you for joining. Let's get right into it. First thing we're going to be covering is obviously kind of the parts of an injection mold. If you look at the pictures here on the right, we see that we have a cavity, often called the A side of the tool. It's going to be forming a lot of your cosmetic surfaces of your part, as well as having your texturing. On the other side, which we call the core, tends to form the backside of the part. It's the backside features, and as those two parts come together of the mold and they separate, we also get what we call the parting line. The core side tends to carry a lot of the actions of the tool and all the inner mechanics, as well as more of the water to help cool the part. And John, you want to go to the runners and gates. This is one of the most important parts of getting plastic into the tool, starting at the sprue, which is where it comes from the machine. If you want to think of this system as a river system, the sprue would be where at the spring or the start of where the plastic comes into the tool, and then it's going to go down the runner system. You can kind of look at that as a river, which the plastic will flow all the way to the end of the part geometry. And then as you get to the end of the runner, you're going to go to the gate. And the gate is what allows the plastic to enter into the actual geometry of the part you are molding. Gating is important. It's to really kind of control how that plastic flows and behaves. Different plastics are going to have different gating opportunities or designs to really control end part finish, to kind of keep some of those flow lines in the shape the plastic that comes into the tool, and kind of control that end surface on your A side of the tool, as we talked about in the previous slide.
Okay. And then I'll jump in here into tight tolerances. Thank you, Orv. So tight tolerances, I mean, this all starts with your overall part design. We see a lot of parts that come through that may be over toleranced. The tolerance or the stack up of your parts, probably one of the most critical things to be looking at, especially when you're dealing with an assembly. next to material choice. So, generally speaking, a tight tolerance for injection molding is plus or minus 2,000 inches roughly. Tight tolerance is a term that's kind of thrown out a lot, and it can vary. So if you don't design your part correctly, looking at materials, the overall design of the part, having a tight tolerance part is going to be difficult to make. And if it's not done right, you can go into just iterations and grooming and trying to get to that perfect part with those tight tolerances. So, key things to think about when you have a part that has tight tolerances, utilizing low shrinkage materials. Materials like polypropylenes or polyethylenes and nylons, they have high shrink rates. And what that means is when you fill the mold with the plastic, as the part cools, there's a shrink factor to it. So, for example, let's use a nylon material. Generally, you'll have a 15 thousandths of an inch per inch shrink. So every inch of part, you can expect 15 thousandths of shrink. So on a 3-inch long part, you can expect 45 thousandths, which can be quite a bit. We take that in consideration when we're designing the molds, but it's a little bit tougher to control than, say, a material with a 3 to 4 thousandth shrink, where you're cutting that in thirds or in a third. Other things to think about, if you have tight tolerances, try to avoid tight tolerances in areas that are around alignment of the mold halves, like the parting line that Orv had mentioned, or areas where you're going to have actions or slides. Those areas can be finicky and tough to control. And then obviously, design your parts in a way to keep those tight tolerance areas off of like sidewalls that are prone to warp or pull in that are unsupported, or easily distorted, which we'll kind of get to in a little bit here further on. Orf?
So material selection obviously is one of the most important parts, and it does dictate where your design is going. One of the most important things is when you're actually looking at what your material is going to be made of, you want to look at the end properties. And every material comes with a data sheet that gives you kind of an overview of what the toughness or strength of that material is going to be, as well as some of the thermal properties that are going to kind of dictate what the end product's performance will be. And you also, from the part geometry side, you want to make sure that if you have a part that is, prone to a high shrink, just, due to the design, you're going to want to select a material that can handle that design, maintain your geometry, and not vary from your tolerances as it's molded. That's when we see a lot of challenges with part design as we go is wrong material selection due to shrinkage or part thicknesses. So material selection is probably one of the #1 things to do as you're moving into injection molding. And we have a lot of different materials out there. You have your standard resins, which are polypropylene, polyethylene, and ABS, which are kind of considered commodity grade. Most of your high volume products for everyday use are made out of these. And then with a lower shrink, higher strength requirements, we go into acetals, nylon, polyesters, polycarbonates, etc., which we would call an engineering grade. And they have a higher temperature, which is, for normal molding. And then we can go even further for even higher performance to a polyether ketone or a PEEK or polyamide imide. These are very high temp, high strength materials. But on the flip side of that, they are, they present different challenges to molding. There's also different additives you can add to your plastic to help give it strength, such as glass fibers, carbon fibers, minerals to increase hardness. We can lubricate it with some PTFE, which is also known as Teflon. There's a lot of different materials, additives that we can put in to really get that resin and that end product to what you want it.
Yep, and there's a lot of materials out there that come preloaded. There's a lot of glass fiber options available. Glass and mineral are probably the two most common, and you're going to see it mostly in nylons. 10%, 30%, 50% glass filled versions of it. But yeah, these can be formulated separately or together, or they can be bought off the shelf with most of these additives already in them. Moving on to draft. So these are kind of the design considerations. So draft on a part, is required. You've got to have your part designed with draft. So the point of the draft is to prevent the part from sticking to the tool. Mainly your cavity half or your A half. So an example above on the top right, you can see there's no draft. So the part kind of fills in the blank space there. So if you have no draft, it's going to want to stick or stay in place into the gray section, the top section, and it's going to fight the core, and the part's going to stick, and it may break. It just may not come out of the mold. You may have to, it just doesn't lead to a good situation. So at a minimum, with us at least, you want to have at least a half a degree of draft, and that will cover most applications. Ideally, you want 1 to 2 degrees. I say 1 to 1.5 to 2 there, but 1 to 2 will get you there. Now, if you have textured surfaces on your exterior part, that would fall into the cavity side. Depending on how aggressive that texture is, you may be required to have 3 to 5 degrees in order for that part to not stick. And then draft on the core side is ideal as well to help eject off the tool, because if you have the same situation as the top kind of left image, that part's going to suck onto the core, and with no draft, the ejection is going to be fighting the part, holding onto the core, and you may get pin push. The ejector pins may bust through the part. Just not a good situation. So a draft is critical to part. Now, I know there's going to be some situations where you cannot have draft, especially tubes, vials. That can be done on a case-by-case basis. Again, it's going to depend on material and design and how the tool is built. So you can do some parts with 0 degree draft, again, just depending on the feature.
Wall thickness. So one of the most important parts with designing your part for injection molding is maintaining as much as possible a uniform wall thickness that allows the part to fill correctly and also pack out, which gives us that uniform density. Now we can work with wall thickness, again, going to what resin you select. That will give you some more stiffness in certain areas, usually with ribbing, which we will cover in a little bit. If you do have extremely thick areas, we would recommend coring that out, which would be removing the material and taking your geometry more to get that uniform shell of your outside shape. And again, as I spoke to before, if you do need extra strength in certain areas, ribs can be added to the back side of the part to really add strength in areas without getting too thick and creating a shrink or a warpage issue, which is going to affect your end part geometry as it comes out of the tool.
All right, thank you. And just one thing to pay attention, in this table here on the right, each material has its own recommended wall thickness. So the key thing when you're starting to design a part is try to nail down the material ahead of time, before you start designing your part, because it can affect the whole design if you switch from one polymer that has a recommended wall thickness that's on the high end versus something that may be on the low end. All right, corners and transitions. So, when material's flowing into the tool, it's almost like a liquid. And liquids don't like hard corners. 90 degree turns, or anything that's going to stop it from flowing. Now, we know you can't always design a part that has a consistent wall thickness, and you're going to have variances. So when you're dealing with transitions, you don't want to have anything, with abrupt stops, kind of like the example in the bottom right corner with the red X. You can see it's a 90 degree, just a hard stop, going from a thick to thin. There's ways around that. You can kind of ramp it, put a soft edge like a rad that'll allow the material to hit it and just keep flowing instead of just smacking into that hard wall. And then a couple other variations of that just to help with the material flow. And when you're dealing with corners, especially with housings, you want to add rads inside and out. There's some specific rules that you can follow. But as long as we have rads in the corners, it's going to help that material flow a lot better. Just reduce the number of, or the knit lines and how they're formed, and the stress in the part. Because anywhere we're going to have like a sharp corner, you're going to introduce stress into the part.
And I would also add that when we're actually machining the tool from metal, there's going to be a minimum radius that our tool can do. Usually it's like very small, but that's also something to consider when you're designing your part. To keep those tooling radiuses, it makes it a much easier transition for us once we go to actually cut the tool.
Good point.
So we touched on ribs a little bit before. One of the things when you're adding a rib, and again, we add ribs to provide stiffness and strength without increasing wall thickness, which allows us to keep our material flow as we talked about before, and it also allows us to fill the part out without having, short shots where that's where the tool doesn't fill out all the way, so we don't have a complete part. But it also, as stated before, really allows us to add strength. And again, when we're talking about a nominal wall that's quite thin with respect to some designs, when you add a rib pack on the back, we start getting the strength that you need from your part. There are some things to consider when you're adding a rib. We'd like to keep the ribs about 60% of the nominal wall thickness. Right there where John has the cursor. If we don't keep that 60% rule as we mold it and the part cools, you'll actually get a shrink mark, and it will actually called a sink mark, where the plastic will actually sink on the A surface of your part and will give you witness lines on that surface. So the way we mitigate that is we try to follow the rule of keeping that rib 60% of your wall thickness. And again, different materials require a little bit different rib design. Like with our glossy materials, we take that 60% and it drops down to 40%. Again, that helps mitigate the sink marks on the A surface and really gives your part a good cosmetic appearance. And again, ribs do have to be drafted, and you usually draft down from that 60% wall thickness down to where they end.
That's right. All right, bosses. These are going to be similar to ribs. Usually bosses are used for some type of locating or mounting, for an assembly, two halves coming together or something being bolted down like a circuit board. The wall thicknesses and heights are the biggest factors of these. They're just basically a round rib if you really look at it. So kind of following the same rules for ribs. They should be, roughly about 60% of the nominal part thickness. And the height of the boss should be no more than 2.5 times the diameter of the hole in the boss. Should be. Obviously, some designs can't follow that, but when you're dealing with that, you may have to look at other things in coring out and dealing with thick sections. And just to add on to bosses, sometimes you want to, either overmold inserts, brass inserts, or, heat stake them in later. When designing those bosses, you just want to make sure that you're following the recommendations by the insert supplier, for the design, the OD or the ID, the requirements for those. Because if the boss is not designed thick enough or correctly, the inserts may not fit or may not hold to what they're supposed to. So something to just keep in mind.
So undercuts, this is one of the, I would say, biggest cost drivers of an injection molding design. If you have an open and closed tool is what we call it, we wouldn't have a part with undercuts per se. So an undercut is any indentation or protrusion that is going to prohibit the ejection of that part without a slide or an action that's going to come in and mold that part from difference in line of draw. And I know when we talked earlier about the mold halves, when you think about those mold halves coming together, if there's an undercut and you would try to separate those mold halves, you would end up breaking the piece or not being able to open the tool because those undercuts are going to lock that in place. Now there's two, commonly characterized an internal undercut or an external undercut, but they all require an extra part to form that. And if you look at the illustration on the side, you can see the top part is a simple tool. There's no side action required because we can mold that hook in the line of draw. If you didn't have that hole there and you would come down, you can see that orange box would actually be the extra tooling action that would have to happen before we could remove that part from the tool to get that snap created. So we really want to try to design our parts with as little undercuts as possible. It simplifies the tool and it reduces complexity and it reduces cost. And John, I don't know if you had anything else to add to that.
No, I mean, you put it well. Just like you said, it's a cost driver, not only to tooling and parts. And you can have different types of tooling. So we've got, manual tooling that we do here for prototype level tools, where this would just be a loose piece within the tool. In a production setting, obviously you'd want something in the line of draw like this, but if it's not possible, you'd want to have it on an automated slide. So, really the difference, you're going to have someone standing at a press, physically removing this and reinstalling it back into the tool versus, the tool, just working by itself. And if you've got a design and not sure how to eliminate an undercut, you can reach out to us. We'll be happy to take a look at the part and see if we can figure something out. Obviously, there's no way to eliminate 100% of the undercuts, but there's things that you can do to kind of minimize them or make them easier. All right, we're getting towards the end here. So this is kind of a best practice checklist. Kind of just going through and highlighting, what Orv and I just went through. So again, when you start designing your part, you want to have your material in mind right from the get-go. And, things that are going to save you, money too in the long run, try to stay to low-cost materials or standard off-the-shelf materials, using standard colors. You can get into colors. We can do, salt and pepper blends here and get custom colors. But for production type part runs, you want to go to pre-colors, which can have a cost associated with them. And again, compare the price of materials, in the beginning. See what makes sense. You could be looking at a nylon that has a really high per pound price. That may just work as well as a standard off-the-shelf nylon. Wall thicknesses, just maintaining uniform wall thickness throughout your part, utilizing ribs to reinforce walls or areas that you're coring out. Just a little, note, 10% increase in wall thickness can increase 33% in stiffness. And as I said, core out unneeded thicknesses and wall stock, and just replace back with ribs to reinforce them. Minimum 1/2 degree of draft, 1 to 2 is ideal. More may be needed for texture. Tight tolerances, utilize low shrink materials. ribs and bosses, design them at approximately 60% of the adjoining wall. Undercuts, again, any type of actions are going to add costs, to the tool and or part. And then corners and transitions, using gradual transitions, stay away from 90-degree turns. And yeah, that covers that. So I don't know if there's any questions.
John, we do have one question. To go back to slide 14, one of our attendees wanted to see that and ask a couple of questions on that. So if we can just leave it there for a moment while they type in their question.
Okay.
While we're there, while we were waiting for him to type in his question, a couple other questions have come in that I think you guys can address at this point. The first one is, the question is, does runner diameter affect the injection pressure?
It can. I mean, typically you have a standard size.
Okay.
Yeah, and it's also going to come down to what your wall thickness of your part is, and how big your part is too. So if you have a really big part, then, and your gate. So big part with the tiny runner system, yes, your injection pressure. Obviously, there's standard sizes that we would use to mitigate that, but yeah, that's going to be more on the mold design side to get the plastic to your geometry.
Okay, so a similar question from the same person is, how about materials? How do they affect the injection pressure?
It's going to come down to what the viscosity of the material is, right? What is the viscosity of the material? What kind of fillers do we have in them? What is affecting that material from flowing? If it's a standard, higher viscosity material, it's going to be different than a really low viscosity, heavily filled material. So it comes down to what your material selection is for your part and your geometry, and then even goes back and builds on your runner type, right? So that's going to affect what kind of runner you need, so we can get that plastic through the gate into the part filled and packed.
Yeah, and I mean, just touching on the viscosity part, I mean, you've got some materials that, almost run like a thick honey versus water. Obviously anything that's going to run really easy is going to fill a part a lot faster with less pressure.
Okay. Is the relationship between depth of part and the draft required?
Yes.
Yeah, I mean, that can have a huge effect on design.
Usually, what is it? Every inch you want to add another ½ degree of draft. It could be more, could be less, according to your part geometry. But the deeper the part, the more draft you're going to need.
Right.
Especially if it's on the A surface or cavity side, and you have a texture on it. It's just, you want to be able to take that part out without damaging the surface that you are trying to achieve.
Okay. The question has come in regarding this slide. In the top image, it appears you're saying that you can make a hole without a slide. Is that so? If so, I don't understand how.
I'm assuming talking about this center here.
I think so.
Yeah, I mean, there's creative ways where you can, it don't really show the inside here, but you're just creating a shutoff, and you can create holes with 2 halves of a tool.
You're basically splitting half of the diameter from the inside and half on the outside. And when you put the 2 together and shut off on that, you do have a void left over.
Right.
Do you have any examples of sink with an incorrect rib design?
Not that we can show, unfortunately, or at least I don't have anything handy.
But we probably have dozens of examples of where this has happened.
Yeah, I mean, I'm sure you can Google rib sink on plastic parts and probably get some images, but yeah, I'm sure I could find something. I mean, we try to mitigate that, from the get-go and prevent that, but it's hard sometimes.
It's basically if you have a lawn and you have moles and that mole trail sinks down, that's exactly what sink looks like. You have a dip in the surface of your part.
Okay. Is the listed draft angle per side?
I'm not sure I follow per side, but
So
yeah, I mean,
you would need 1/2 degree on each side of that. Yeah, it's
yes.
not split between the two. So if we require 1.5 degrees of draft, it's going to be every wall that's going to be separating or needing to be pulled in the perpendicular of a line of draw.
Okay. What is a good rule of thumb for determining the decision to go with either a slide or a pick out?
That's usually driven by the project. Usually pickouts are for lower volume prototype, form function type parts. Anything that's, I would say, 500 pieces a year or less. Once you get above that, you want to start looking at automated slides, actions.
All right. Follow up to the question about the runner diameter. Said, why ask runner diameter? Because if your part is big and your runner diameter is small, then your runner can cause fill cavity. I'm not exactly, I can't quite tell what they're asking here. Seems like your runner can cause the cavity not to fill.
Yeah, I'm not sure.
Right. What material tool yields low cost tooling for low volume? Galvanized rubber?
I mean, with our tooling, we use a QC10 aluminum. It's a high grade aluminum. It's cheap, it's fast, easy to cut. You can run cooling. It does cooling well. That's what we use for our prototype and low volume tools. And it holds up pretty well. I mean, unless you're dealing with a high glass content nylon or any type of glass filler, it can wear on the tool a little bit faster than, say, like ABS or polycarbonate.
Okay. Does a part design need to incorporate features for the point of or site of injection?
No. But you should take that into consideration in designing it and, how it might be gated, depending on if it's a cosmetic part, non-cosmetic, and that stuff that we can help with. Most of your production type parts, high volume parts, million pieces plus are used with hot runner systems, which we can do, but we don't do a ton of them because that's more for high volume. Most of the gates we do are edge gates, so they'll be visible along the parting line or the outside of the part. You can do sub gates for cosmetic type parts, and there's a couple other gate types, but you should be thinking about it. You don't necessarily have to design it in, but be thinking about it when designing.
And just to reiterate, that's especially on cosmetic parts, you're going to want, and again, most gating is going to be done on the B side of the part too. We tend not to gate through the A surface. So a lot of times it's just an additional kind of mold design thing.
Yeah, so if this, take this part for example, if this was a cosmetic part on the outside, this darker orange, an edge gate would run up to the outside of the part here and leave a small vestige, which may or may not be acceptable. If it's not acceptable and you want a nice clean surface on the outside, we would have to subgate to somewhere on the inside of the part, or on this surface underneath here, with a cashew gate or something. So it's really going to come down to the part and the end use.
Two questions about sync. The first one is just an understanding of sync. Is sync when you can see it on the A side?
Sync can be anywhere. It's a void in the part. So, as the material's cooling, so if you have a thick section of plastic, that thick section is cooling at a slower rate than the thinner areas. And what's happening is the material's pulling away from itself. It may look like a bubble or sink, but it's actually material. It's just a void in the part. But it can appear anywhere. It's where thick sections are. I mean, they're most common, going to be, like ribs, bosses. Those are, formed on the core half, but they'll show through to the cavity side or the A side of the part.
Can sink marks be lessened by cooling the part longer before ejecting it?
Or if you want to take that one.
Yes and no. Again, it's going to come down. It really, if you really want to stick with the 60% or 40%, depending on resin, the plastic is still going to want to behave and cool in those thick areas. So a slower cooling time may mitigate that some, but if you're still too thick, you're still going to be seeing those sink marks.
Yeah, then you're starting to get into overpacking the tool to try to pack enough material in there so when it does cool, it minimizes that, but that can lead to other issues with the part, flashing the parting line, messing with dimensionals. You're trying to force it to do something that it's not supposed to do.
Right, and for those that don't know, flashing the parting line is where you actually push plastic out between where the mold halves come together. It's like you're actually over pressurizing the tool and you're squirting plastic through the half of the mold. So it's something that has to be trimmed. It may not even be able to be trimmed. It really affects end part quality.
So yeah, in the end, I mean, you want to just minimize those thick areas, core them out, and just try to follow the basic rules.
All right. Can you explain tunable tool inserts in the case a few geometries need to be evaluated?
I can only assume, I think. So I'm assuming it's, a few inserts that, we're just tweaking or grooming to meet a certain spec. I mean, I'm not sure how to answer that.
Maybe John, he's asking about, he's got different inserts that would go into the part so that they can evaluate two different types of geometries,
Okay.
maybe off the same mold.
I mean, if that's the case, yeah, I mean, we do that quite a bit. So, there's a lot of devices that may take, a couple different IDs, and if the geometry, it makes sense, we can do swappable inserts to create, multiple designs out of one tool. In doing that, you can introduce, witness lines or parting lines where, depending on how that insert's created or the design of the part, that would be the only drawback.
Okay. Clarification about one of the questions above that we couldn't figure out. The point was, if your diameter of the runners and gate is too small, can it cause issues with material filling?
Yes. But I mean, we usually don't have that issue. I mean, I've never seen it.
Sorry, John.
No, I was just saying I've never seen that issue before.
Okay. How are two bosses for, say, screws, which are perpendicular to each other, molded, like on the inside of a box, like a chassis?
Two bosses perpendicular to each other.
Yeah,
I'm not sure. I mean, it's.
I think what he's asking is, so in the image there, you've got a one that's pointing up, and how would you have one that maybe is pointing 90 degrees away from that? So
I mean, that would be an action in the tool then. I mean, I'm assuming it'd be something similar to like this. So you'd have a boss in the corner and this hole through the side. I mean, it would be an action. If it's not in the line of draw, it would require an action, either internal or external.
Okay.
Yeah.
What is the effect in geometry of cooling your part too fast?
Thermal deformation. You're going to experience some warpage, especially if you have a larger, flatter part with not adequate ribbing. That part's, if for the box, for instance, here, it's going to want to shrink in and almost bend into itself.
Bow in on these sidewalls.
Yeah. And it's also going to, when you cool too fast, it creates issues such as, it's tougher to get the part out of the tool. The tool may shrink and lock itself onto the core. There's a lot of issues there, which, as we process these materials and we have these material data sheets and process parameters, we can usually mitigate most of those. Again, comes down to part design and material selection.
Okay, just a couple more questions. What are the major design changes needed for a part design for 3D printing, but that now I want to create for injection molding?
So you're going to want to, one of the biggest challenges I see with a 3D printed part going to injection molding is making sure you don't have any voids in the part, undercuts, and your nominal wall thickness is uniform. A lot of 3D printed parts, it's a layer-based system, and you don't have the challenges of high pressure, high heat forming the part. So I see a lot of extreme thicknesses that work for 3D printing, but wouldn't work for injection molding, and then undercuts. The whole geometry may be undercut. With 3D printing, you can almost form a part within a part. Going to injection molding, we want to make sure that we have everything open to the line of draw. And again, your wall thickness nominal is thin with respect to what material you're selecting, and your undercuts are mitigated as much as possible.
What is the best software or application for injection mold analysis? And I'm not sure that we are the right ones to say what's the best software, but we can certainly say what we use.
We use MoldFlow, correct, John?
Correct.
So it's a very powerful system, and in the right hands, it can tell you fairly accurately if your part design is pretty much locked in. Some of the challenges or successes you may have when you actually go to injection mold it.
What are the different prototype options for alpha parts? So when we're looking for looking at fit, form, and function, and then beta, reliability and strength prior to committing to production tooling.
Well, I mean, for alpha parts, I mean, you got CNC, you've got 3D printing, you've got RTV molding. Once you start getting into your beta parts, I would probably move to a prototype injection mold tool or our RTV molding. You've got a little bit more material choice there. It's not going to be the exact grade of material for RTV molding, but they're going to be like materials. They'll have the same properties, just not the same chemical makeup. So if it's just strength and that may be a good choice, but if you're looking for something, the chemical properties, you'll have to just go with the engineering grade resin and just move to molding into like a single cavity prototype tool of some sort.
Last question, as we're running out of time here. Do slides always have to have an action to the outboard side of the part?
Can you repeat that?
Do slides always have to have an action to the outboard side of the part?
Yes, I think.
We can do internal. We can do internal
Yeah,
action.
I mean, well, usually it's lifters. If you got internal, say you're going to capture this hole from the interior of the part, you would end up with a lifter. If you're going to capture it from the exterior of the part, then it would be a slide. So anything, on the outside of the part typically is a slide. Internal undercuts are created by lifters in the automated setting.
Okay. So there were a few people who asked about links or how to get our injection molding best practices. Somebody else was asking about a copy of the slide deck. We have recorded this. There will be a recording that goes out within 48 hours. I will be including links to the injection molding best practices and to the material shrinkage list. Also, this presentation and the one to follow in June are come from our Design for Manufacturability handbook, and I'll include a link to that as well, so that everybody has a copy of all of these resources at your fingertips. We thank you very much for joining us today. Appreciate your time, and we'll be getting out a link, as I said, to this recording within 48 hours. And then if you have any further questions about the topics presented today, please email us at info@eccentricmold.com. Thanks, everyone, and have a great day.
Thank you, everyone.
Thanks everybody for joining.